Let's continue. So the next part we're going to deal with how to tell you how to do the inference and learning. So again, as I say, I want to emphasize this procedure of the statistical data analysis involves modeling and the model assessment and then interpretation. So the modeling part, obviously, you need to make a certain assumption. And there's a famous quote by statistician George Box. What he says is that all models are wrong but some are useful. Because you don't know the true model. You never have the ground truth when you have the, during the experimental data. So essentially you make some assumption. And unfortunately you don't have the ground truth, so all the models are wrong. But some are useful for the specific, for your purpose. So the goal of the data analysis is that try to infer the unknowns. The unknown could involve the model, you don't know, the model parameter, the uncertainty of the data. For example, you're doing the prediction and the future data. Also the data structure, if you want to do infer the data structure. This slide I put it here just I want to give you some sort of philosophical sort of idea of what's involves the learning. The learning part, in generally, combines three parts. One is the estimation. Estimation basically involves a statistical problem. You want to see a hypothesis among a very large hypothesis space. And obviously your hypothesis is very small. Right? So approximation is a representation problem. So then you want to, given that certain hypothesis, you want to approximate the hypothesis according to some criteria. Then, because you deal with approximation, then you have a trade-off of the bias and variance, right? During the statistical estimation, you have the bias and variance. And then finally, because you have this, once you have write down everything, you need to do optimization. The optimization is basically just numerically solve the problem, solving the cost function. And define the cost function, and then the optimization procedure defines the learning rule. So for example, give me some data, as I showed you, try to model the neural response. In the many slides before I showed you the generalized linear model. Using generalized linear model is one of the small class to model the neural response. So you're using that, you define the hypothesis space, so generalized linear model. So you define a certain hypothesis. Then you do some approximation. You represent what's the variable you want to fit the generalized linear model. You can incorporate certain term, using the spike history of its own, or spike history of the other neurons, or certain stimulus input variable. And you do some approximation. You define how many order you need to model that response. And you have the generalized linear model with a different model term. By using the higher order, basically you have a lower bias, a high variance. And using the lower order, probably you have a high bias and low variance. So you deal with the variance, bias variance, representation problem. And finally, the GLM, you need to estimate the GLM parameter, then you deal with the optimization problem. So what we tell you before is using sort of Newton method or conjugate gradient method to solve that optimization problem if you have identifies the global solution. And this is an example of that. And there are two basic approaches for solving this state and parameter estimation in the state space analysis. One is the likelihood approach, and the other is the Bayesian approach. And likelihood approach is very well established in statistics. Have a lot of nice property, like symptotic property, when you have a very large number of samples. Unfortunately, when you're doing the neuroscience data, this likelihood approach sometimes is questionable. The assumption is questionable because the symptotic property. So you have consistency, normality, and efficiency. Another important property is the functional invariance, which means you parameterize it. You have the theta, so theta is your estimate. If you have a maximum likelihood estimate theta, so you have another function, and this one estimate, you just plug into your theta estimate. Will be your optimal. This is your maximum likelihood estimate. because during with you just plug in the maximum likely estimate after the transformation and reparameterization, you still give the you still have the optimality of the maximum likelihood. Unfortunately, maximum likelihood, you're using a large model, a complex model, you have the data overfitting problem, which is actually, we show you earlier, there's a generalized linear model, just using maximum likelihood. You typically do the overfitting problem. And on contrast, the Bayesian approach, just the philosophy is just try to using the data, let the data speak for itself. So you try to estimate the full posterior. And because of that, you actually avoid the overfitting principle. You should not have overfitting, basically. You might have the prior, you define the prior, which is little subjective. But if the prior, you believe the prior, your prior is correct, and then basically you already integrate out all the possibilities, so you should not have the overfitting problem. So it's important to point out is, I listened to the talk by Zhe Chen, he actually pointed out that, people normally say using Bayesian is a model of the random variable. So he preferred using uncertain variable, not random variable. The reason for that, the idea of Bayesian estimate is trying to infer the uncertainty of the unknown variable. So the unknown variable, in the Bayesian way, typically try to treat everything unknown as a random variable. But he preferred, and Zhe Chen preferred using the term uncertain rather than random. Because imagine that you have a pi, for example, pi 3.14, blah, blah, blah. This is actually deterministic, right? Once you know, it should be deterministic. But because you don't know, like after the first 100 number was the 101 number, you don't know. So because you have some uncertainty there, the variable itself is not random. So basically, if you have some information, you can write down the probability because the 100 numerical value was the value that you have the probability of that. So the probability obviously is, it's very, when you give some information, probably with a high probability that the value should be correct. But maybe someone just by mistake can write that variable wrong. So there's small probability that value you see could be wrong. So it's just uncertain. The uncertainty could be very low, but it's not zero. So the uncertainty basically is not necessarily random variable. So I recommend some book for this inference. You can just go through it and give you some sort of a textbook guideline how to do those sort of inference. It doesn't necessarily give you the example, neuron science example, but give you some sort of basic about likelihood inference and Bayesian inference. So when we do the likelihood is essentially just a function, a probability of the data as a function of the parameter, basically define the likelihood of the parameter. So theta here is the parameter. So the y is the observed variable, x is the theta variable. So the observed data likelihood basically saying, given the unobserved variable in theta, what's the probability of you observe y given x in theta. And then maximize that, basically, you have the maximum likely inference. And when you write down x and y in this part, x, y conditional theta, this is called complete data, this is observed data likelihood. And the EM algorithm, we will talk about later, is basically when you take this expected complete data likelihood with respect to your unknown variable x. And this could be a process, x. You take the log of the complete data likelihood, take the expectation of the hidden variable, then you define this as a Q function. In the Bayesian inference, the variation of Bayesian inference, typically deal with this marginal likelihood. So marginal likelihood is only estimate Py, so you need to integrate, in order to calculate this term, you need to integrate the theta, which is the random variable, you put a y on that random variable, and you also integrate x. So you need to do integration about x and y, so to do the Bayesian inference. As I say, the EM algorithm basically is a framework to estimate this unknown variable using maximum likelihood. So the key of the EM algorithm consists of two steps, E step and B step. The E step basically, you want to compute the complete data likelihood. as I showed previous slide. And it's based on your certain estimate. So EM is an iterative estimate. You come with some initial condition of theta, you run this E step, M step iteratively. So the E step compute this Q function given this theta K, you compute the theta, compute that. And then after that, you compute the expected statistic with respect to the latent process X. So for example, in the linear Gaussian case, you need to compute the X squared xt times X plus 1, the variance and the mean and the cross correlation. And this second order statistic when this X is a linear Gaussian variable. So the M step, basically, when you update the theta to theta K plus 1, and the solve is a maximum, so the maximum problem, producing the theta K plus 1, and which is a point estimate. So you only have one point, it's a point estimate. And then this EM step, essentially, to solve this maximum problem, basically you just solve this if you have a fixed point equation, take the derivative of Q with respect to theta and set it to 0. And if this have a analytical form, you have an analytical solution, closed form solution. If it doesn't, you just solve it numerically using the gradient or Newton algorithm to solve the equation. So the good property of the EM is basically by doing this iteratively, every step you only guarantee to increase the likelihood or log likelihood. So that if the likelihood have multiple until when the algorithm converge, you converge to the local maximum. Unfortunately, EM algorithm have because the hidden variable. So typically you have, I think for most of the problem you only have a local maximum. You don't have a global maximum for most of the problem. And also, as I say, the solve is two-step, and sometimes you cannot solve it analytically. Like you take the expectation, then you probably need to replace by Monte Carlo simulation in the E step, or solve this as a Monte Carlo in M step, or vice versa. And this could be an exact approximate, and you have different extension of the EM algorithm. Also a few pointers about the link of the EM algorithm to other literature. For example, majorized maximization is basically is a broader cast of the EM. So instead of maximize the likelihood, we basically try to maximize a surrogate function, which is a lower bound of the likelihood. And because you maximize the lower bound, you still increasing the likelihood, but unfortunately you might have some gap between then you have strong bias because it's a surrogate function. The motivation of that essentially is the likelihood sometimes is not a concave function. So using the surrogate function, if it's a concave function, it's better for the optimization. The people also in the literature tell you that EM can be interpreted as a variational sort of technique. Then you try to maximize the free energy. And later on, I have one slide to show you how to link the EM to variational method. EM also works well, not only works well for state space type model, which is a dynamic model. It also works well for some static model, like for example, you do a Gaussian picture model, which is a static model, and you still can use an EM to solve it. There's some sort of philosophical sort of interpretation of EM, and then show its link to the Bayesian, and see how to link the EM to the Bayesian estimate. So for example, Gibbs sampling basically can be interpreted as another way the EM by using auxiliary variable. You simulate the data, and you go through this E step, M step. It's a special case. So the Bayesian basically, as I say, go for the state estimate, go back to the state space model now. Do the state estimate, calculate the posterior distribution. Then the posterior, you can calculate the posterior mean, mode, variance, predicted posterior. So for example, here, if it's a unimodal and it's a bimodal case, then you can have different sort of mode, two mode, but it's a maximum mode, then the mean, and sometimes you have the median. To search for the modes, actually, if it is high dimensional space, not necessarily easy. If the mode, you cannot directly maximize it. So the three basic operations you need to involve to compute the Bayesian estimate. One is the normalization, because you need to deal with this conditional probability. This is the product giving the joy probability, and this is the normalization term. The marginalization, integrate of the unobserved variable, and Z. If the Z is not analytical, it doesn't necessarily give you, integral form, so you might have a numerical solution because the Z is not fully integrable. And then you have expectation, when you calculate some sort of expected statistic given the certain function which is, for example, x is fx, it could be x, then you define the mean variable. Unfortunately, most of the integration here is computationally intractable except for some special case, for example, Gaussian variable. And then because those integration will show you previously, and then because it's a non-computationally intractable in many cases, then you have different sort of approximation using approximate Bayesian. And I did some sort of a few method here, which is not exhaustive. So Gaussian approximation and mean field variation approximation, expectation propagation, and those three methods, deterministic approach. And then also Monte-Carlo simulation, which is stochastic. I'm going to, in the rest of the slide, I'm going to go through those very, give you a high level overview of those techniques without going to very detailed, specific detail. Because you see many, in these days, in neuroscience analysis, those techniques are widely used for the inference. At the end, basically, I will conclude. At the end, basically, you see to choosing which method you're going to use, you're basically facing a trade-off between the speed and the accuracy, and then which method is optimal. It's very hard to make a general conclusion. It really depends on your data, depends on the structure of the data. So first of technique, so-called Gaussian approximation or plus approximation. And the plus approximation in the literature, the numerical literature, is also called saddle-point approximation. So what it does is just do a Taylor expansion around the mode. So essentially you have a non-Gaussian sort of multimodal bar. You have a maximum mode, you find a mode, and do a Gaussian approximation around that. So imagine that you do a log fx, you do a Taylor series expansion in the first term, and this first term basically when the saddle point in the maximum is equal to 0. And then you only have the second term here. So then you can do some algebra, and you can move the size out, move on the side out, and then you have this constant term, and approximate by this term. And this term is basically your Gaussian form around the expansion around the mode x max. So the first order Laplace method basically is the procedure basically find local maximum x max given certain PDF fx, and then calculate the variance and take the second order derivative, calculate the variance, take the negative inverse of the Hessian information. And you approximate this PDF with this mode x max and the variance. This is a first order Laplace method. And also people in the literature, statistical literature, also have second order Laplace method, which is a little more more complex. However, in this work by Koyama, I think he's now in this institute as well. He did some work with Rob Katz and at Carnegie Mellon University. They showed that in the neuroscience application, this is the second order Laplace method. They found that the statistical inherent method, statistical error of the posterior is actually often larger than the numerical error of the first order approximation. Which the conclusion is that unless you're doing simulation, unless you're doing a theoretical simulation, and you see some gap benefit of that second order approximation. But when you deal with this real data and the approximation, the benefit you see, which is negligible, basically, which is justify the first order Gaussian approximation. So I want to give you one example to show you how to do the sort of how to do this inference. So imagine that the state equation given by a first order AR scalar, and the log rate, which is your model is a generalized linear model. The log rate basically is the in the generalized linear model, log rate is basically is your eta, is a natural parameter. Then associated with some mean, a baseline final rate mu, and alpha. This is a Markov. So basically, this is a Markov process x. So the rate is modulated by a Markov process. So you can say it's the rate is the double stochastic. This is stochastic by the y observation, and then also this is a Markov Gaussian process. Then you have another ut, which is imagine it's an observed variable, control or input variable, and you observe associated with some regression pattern. So for that, you can write down the point process. So what you observe is 0, 1 observation. So you can write down the observed data likelihood in this form. So dyt basically is indicator variable, which is at dt, this indicator variable tells you if there's a spike, it's equal to 1 or otherwise 0. And then you also write down, given this twofold, you write down the complete data likelihood, which is social state. This defined by the Gaussian sort of first order linear Gaussian process. And this price the observed likelihood, and you combine these two terms, give you the complete data likelihood. So imagine that you want to do an EM, then the complete likelihood. In this case, you probably need to do a Gaussian approximation because this part is not, if you write a likelihood function, it's not concave function with respect to the unknown parameter alpha, beta, and those are your parameters of interest you want to estimate them. So probably then you need to do a Gaussian approximation because your likelihood is not Gaussian. So in this the state space format, basically, as I say, to do the Gaussian approximation, you need to calculate the Hessian information. You have the probability in this posterior. Then you estimate the second order, so the second order statistic, second order the derivative, Hessian information with respect to your unknown variable x. Then you have this sort of complex form here showing for this specific application actually involves multiple spine trace C, multiple neuron case. So the previous example C equals to 1. Then you do a Gaussian approximation on the log posterior. Then you need to calculate this sort of this is you get a mode. Then you also need to know the variance. And you can update the variance. Then you have the when you have the mean, mode, and variance, then you have the Gaussian approximation and log posterior. For that, then you can run when you do the Gaussian approximation, you can get this point process filter, which is a similar analog of the common filtering. In the state equation, the prediction, you still have similar for the common filtering. The one-step mean prediction and the one-step variance prediction. This is the first order AR process here. And then you see some sort of in the posterior update, also will be different from the common filtering because you have non-Gaussian likelihood in the observation equation. So in the posterior mode update, just plug in the previous estimate and then update it. This is similar. And this part, you can think this part is the innovation term. So the observation for dy is indicator variable, whether either 1 or 0, depends if you have a spine or not. And this part is your rate, plug in rate estimate, exponential. Log rate equal to this linear part, times the delta, which you the probability, given the rate condition density function, times the delta, give the probability you observe spine or not. So then you have 0 or 1 here, and then minus the probability variable, which is between 0 and 1, divide the innovation term. And then you can have a think about, then you have an error correction term, you have a common gain, which is this term in this example, we can derive it. And then based on the Gaussian approximation, you update the variance here. Unfortunately, for this part update, actually this is non-linear, this update, because this part involves the posterior here, which is this part. And then eventually you need to rely on the numerical method to solve it. For the Gaussian, for the Bayesian estimate, in some, it's important to define certain prior. So then, one of the important prior is called conjugate prior. The property of conjugate prior basically gives the property if the posterior, if the prior have the conjugate for the likelihood and the posterior have the same form of the prior. This, you can think about the analogy of the operator theory as an eigenfunction. She is an operator, the prior, and it's an operator will transfer to the posterior and have the same form. And the hyperparameter of the prior basically is a pseudo observation. And then when you have the likelihood function, if you want the exponential family I tell you about earlier before, then have the conjugate prior, then you have a sort of a natural, a broadcast of the distribution that have the conjugate prior. So for example, and this is the, say the data X have the sort of a binomial form. So this is actually, it's a proportional, because I have a normalization constant. Then you define this Q, which is the probability Q is the parameter you want to estimate. You assume some beta distribution. AB is the hyperparameter. Then have this form. So essentially this form and this form have some Sievers is the functional form. Then the product of this prior and the likelihood will give you an updated posterior. And this is analytical because they have the same functional form. You can update the hyperparameter here, A and B, and then you can write down the analytical. So the variation approximation technique basically exploits this property, the conjugate property. So you can think of variation of Bayesian or variation of Bayes is the basic extension of EM. In the M step, the difference of the M step replaces this point estimate with the full posterior estimate. So then you apply some sort of, assuming some conjugate prior for the parameter theta. So in M step, VB M step, you can update the posterior of the theta rather than give a point estimate. In addition to that, another idea is basically estimate the lower bound of marginal likelihood associated. So you want to integrate all those unknown variables with the marginal likelihood rather than the likelihood itself. So the issue of the VB, I don't know how many people have knowledge of the variation of Bayes, which unfortunately in the tutorial, in the second part of the talk in the afternoon, actually have some example, a specific example using variation of Bayes to do the inference. And so there's some issue of variation of Bayesian inference, even you have a very nice property, but you have to be aware of the estimate. So because you're dealing with this assumption, a lower bound and a factorial posterior assumption, then you're dealing with the bound could be very loose, especially in mean field approximation. And could be biased because you don't directly estimate the likelihood, you estimate the bound of the low marginal likelihood. And the variance uncertainty could be underestimated. So typically you underestimate the variance when using the variational bound because you're still in the factorial form. So you have some, if you, the parameter actually is not fully factorial, so which have some dependency. When you still in some structure, basically you minimize variance by assuming certain structure. This is just very quick sort of like a quick derivation. I won't be going into detail. So you have some observed variable x. So then you have this x in general is observed, could be a parameter or state. And the variational distribution you define, this is your estimate of this posterior x condition given y is your posterior of interest. So you assume the variational distribution qx. You approximate this, right? So what you do is minimize the Kuiper divergence of this and define as a negative free energy and a log of the marginal likelihood, Px. So you change the force, so you maximize the free energy, basically is the lower bound of the marginal likelihood because this term is always non-negative. So the mean field approximation, it basically assumes x has many terms, right? Assume x is a factorial form of the mean field approximation, it's a product. So it has certain structure. It doesn't have to be mean field, but mean field is one of the special case. You can have some structure, there's more structure, there's some dependence between x. You have like a block structure. But the simple form is the mean field approximation. So what you did to solving this, minimize this Kuiper divergence, basically you want to find a Q and solve this Q equal risk impact x0 and update the two series. Then it's very similar to EM because the E step and M, the only difference in M step basically you want to, because this function FQ is actually right now is a functional, because the argument is a function, it's a probability density function, rather than, so you're actually doing a functional optimization problem. So the M step basically you want to take the derivative respect to the function, probability density function, and then and give you the solution. And I want to say that because you see the difference here, the Kuiper divergence is non-symmetric, so you in this case actually minimize the proposal distribution, variation distribution with respect to P. If you change the form P to Q, you have a different approximation, which is give the expectation propagation. So it depends on how you write down the Kuiper divergence. The solution could be very different. And this is also a very quick sort of summary of the expectation propagation. So in a state space for people sometimes write down some factor graph. And I'm aware of, I'm jumping to the factor graph, it's kind of a completely different concept because the motivation right down the graphical model is a graph. Factor graph basically is this has some link to the communication, communication. But if you think about this as a graph, so the x is one of the random variables that you have, have a link, the past, and the future, and then some observation. You can write down three terms. And the probability graph of this Px is proportional to the factor of this 2 to 3 term. So, because in general, this probability function is non-Gaussian. So, dealing with them, so this term, the likelihood could be non-Gaussian likelihood. This could be Gaussian, this Gaussian, but this, in general, is you don't know, so it could be non-Gaussian. So you approximate the individual term by a Gaussian product. Then you can have this Qx is a product of the Gaussian. Right. This idea comes from Tom Winker's when he did a PhD at MIT and now he's in Microsoft research. Then you basically write down a form of the approximation by 3 terms. And then how to find out this 3-term Gaussian approximation. You deal with the numerical, and I will show you here. The key idea of the expectation propagation is basically trying to change the global divergence to the local divergence. So here is actually, originally you want to optimize Px respect to the Kuiper divergence of the Px respect to Qx. Qx is the product of this 3 term. And this is the original term, it's non-Gaussian. So instead of write down the global term, because this is the true form, the product of the original term, and this is, then you want to replace that with a local divergence, which is you fix the other 2 terms and update by a best estimate. So for example, here, you want to find, you replace Ax. So you replace this term, you replace one of the term by the approximation, and make the other fix. And basically, So you fix one term and update, fix the other two terms, update one of the term, and find the best estimate, local estimate of what's the best approximation, and then rotate it. And then when you get this update, and fix the other two and update one. And basically replaced by a global divergence with a local divergence. So this is the original term F. This is the original term approximation, but this part doesn't change. Now you replace one of the term by the true and the other using approximation. Then you only update one of the term of the product in term, and then iterate the process until this divergence is minimized. So then you can say that, for example, you'll be surprised the solution is quite different. So you have a non-Gaussian probability function, and then if you do a moment matching, they give you this sort of best Gaussian estimate here, this line. And the expectation propagation, this best Gaussian using moment matching basically is a global estimate. You find the best estimate using the matching the moment statistic. But the EP or expectation propagation basically give a different estimate. Normally it's better. The intuition is that when you're doing a local approximation, especially the mode, have a multiple mode, then it should be better. And this can be illustrated by this slide. For example, you have a product, so this term times this term, you want to basically imagine that this term, one of the factor term is this term. And if you do it in a naive way of approximation, you probably approximate by this red approximation. Then this term, this red curve times this curve, you will get something like that, the red. And the true is the blue, right? So this estimate is not necessarily the best estimate. So what it does, if you do it in a smart way, doing the informative way of the approximation, you don't approximate this way, you approximate the Gaussian by this way. Because these two parts are more close, and you get something like that. And this red curve will be close to the true estimate. So essentially, you replace the local divergence rather than a global divergence. You don't want to do a global estimation rather than a local estimation. So still have the material, the Monte Carlo particle filter, and have some MCMC. So I'm going to quickly go over the Monte Carlo simulation and conclude the part of the inference method, and go into the last part of the neuroscience example, because I think the audience of interest, the last part may be more interesting. So particle filter basically try to do the Monte Carlo simulation. We try to use simulate the particle from the posterior, and for a point mass approximation of the posterior. And you propagate this particle to the state equation. You have the particle sample from the previous posterior. Then you have certain state equation, and also have measurement equation. You propagate it. You get different sort of a point, and there's no represent the importance. The high likelihood will here have a large area, a large node. Then you do resampling. Because those part important that you want to resample it according to the weight. And then propagate it, say this particle go to the next step. Although it's very intuitive by this graph, unfortunately in practice there's some issue, which is during the variance issue. Again, this is important sampling idea replaced by the sampling, calculate the integral of this f, so expectation, replaced by a ratio px divided by qx. So you sample the weight by using the importance weight wx, which is this ratio. Then using this Monte Carlo estimate replaced by the true estimate. Then you have the variance of that. There's an analytical for the variance. So when you're doing the recursive way, basically the variance w times the previous weights, and given by this base part, like group times the prior, normalized by the proposal distribution. The question is that how to choose the proposal distribution, and that's the key. How to minimize the variance. Because if you this cube choosing poorly, and then the weight, most of the weight will be 0, so it will be very bad, less informative. Because all of your information are represented by this wave function, wave x. Because you're using the wave function to calculate the posterior using a point mass approximation. So all of your information are preserved in those weight. You know, if those weight are dominantly some of the term only 1, the rest of the term 0, so it's very inefficient to represent the mass. So then you have different way to choosing the proposal distribution. One simple way is using this one equal to the prior, then this cancel out with using this prior, then you only proportion to the likelihood, right? This is another alternative. This basically using a scalar, so the exponent scaling, scale the weights. Then there are other ways to which I won't be able to go into in detail. So you can use some auxiliary variable and then basically sample using sort of information about the observation. Because this proposal distribution here depends on, not only depends on the history, it also depends on the current y. You actually observe current y. So what is the information, what's the current y tell you about the current state estimate? So you have to use the observation to tell you something about the current state. So the optimal basically is the conditional, should be the true variable. But because you don't know the true conditional probability, then you have to use an approximation. So the idea of the auxiliary variable is basically just a sample some auxiliary variable, depends on the y, and then the sample again is a two-step process in sample x, conditional on this auxiliary variable and y. And hopefully this process is informally tell you something about the y, so the variance should be slower, reduce the variance. So this slide is showing how to do Bayesian. The Bayesian is when you're doing the Foley Bayesian, basically you want to estimate the full probability, the full posterior probability of the state, parameter, everything unknown with the model size, and then assume certain prior. So you can write down everything unknown as a theta, x is the state, then you assuming, for simplicity, you're assuming this 2 factorial. You want to estimate between separate, and you have the likelihood term, apply on x, apply on the theta, and then this marginal, sort of a marginal likelihood. You have to integrate everything out. So this term is the difficulty term. Right? Estimate this a marginal likelihood. So give a sampling, probably just show you this example. Give a sampling, basically, you can think is a simple way to draw a sample from this joy probability x. X here could be a general, could be a theta as well. So then you, in the 2-dimensional case, you can think of it as an iterative process. A sample, because joy probability might be difficult to sample from, but sample from the conditional probability. So sample conditional x to sample x1, and then vice versa. Then eventually you run a Markov chain, and then hopefully when given sufficient learning period of the sampling, then the final estimate reach the target posterior, which is the equilibrium. So one of the application of the Markov, some MCNC Markov chain process is the important question. Like for example, here is one question is how to estimate the rate function or PSTH, how to adapt the bandwidth. Right? I think Professor Shigeru Shimamoto and Hideaki, they did some work on this, how to adapt choosing the bandwidth to estimate the rate function. This is one of the solutions using come up with some estimate of how to choose adaptively update the bandwidth to estimate this rate condition depends on the rate. In the literature, there's a method of Bayesian adaptive regression supply bars. using the Bayesian way, Markov chain color method, estimate that basically you need to identify the spline location, and make it smooth. Right? Essentially, how to smooth this rate function and get the ideal. How to basically choose an adaptive bandwidth by choosing the where to put this knot location of the spline. This is the graph to compare the bars and the kernel density estimator. You can check literature how to do it. For the MCMC part, I recommend these two books if people want to explore the detail of how to do the Markov chain color for the inference problem. So this part, hopefully I give you, even it's very brief, hopefully I give you some high level sort of information how to, during the dual estimation problem, the state estimation and the parameter estimation, what's the principal way to doing that. So EM, for the maximum likelihood principle, EM is a principal way to deal with the missing variable estimation. You want to do the Bayesian estimate, essentially put some prior on the parameter, and depends on you want to do what kind of Bayesian, either it's a Foley Bayesian, using the Markov chain monocolor, or doing some approximation, and then you estimate either the marginal likelihood or a different kind of cost function. And you see different kind of cost function give a different solution, either expectation propagation or variation of base. And obviously then they have some sort of pros and cons, depends on which approach you use. At the end, which approach you use, the EU basically is your choice. The trade-off between the accuracy of the solution and the computational issue, how to choosing the right solution really depends on the specific problem. The ultimate goal of the inference, obviously you want to come with a very fast, scalable, which is a large scale problem, and robust, which is dealing with a lower variance, a higher generalization ability. So the last part, in the last hopefully 20 minutes, I will give you some application, and hopefully will convince you, give you more information how to do using this state-space modeling for the neuron size application. For neuron size data, essentially you want to analyze that, you basically want to come up with some method to characterize this neural response. You measure the neural response, which could be different neural response, could be intracellular recording or extracellular recording, could be spike train, local field potential, EEG, or fMRI, calcium imaging, even behavior data, like reaction time, or behavior response, either correct, incorrect, 0-1 response. So you want to build a model to characterize those data, the statistical property data. And there are several examples. Hopefully, I can go through them. If I can't, just I have to skip some of the examples. I just go to it. So one of the examples is the neural decoding problem using hippocampus. So imagine that this process, the cartoon process, you have the animal running through the maze, the open field environment. So you have a spike activity. After spike sorting, you have a spike activity. So the encoding process, encoding has you construct a receptor field, a place field. Then you have this 3-cell, you have a place field. Then in the decoding process, basically given the spike, you have this receptor field, and you come up with the Bayesian estimate, come up with the Bayesian decoding algorithm to estimate the position. And that's the procedure. So the encoding part, generally, for here, we can assume in the rest, the position is in 2-dimensional, is a random walk process or AR model. So you have to fit this sort of position path model, given the training data. You have the encoding to train data. Then you model the receptor field, which is, I show you here, it's just this color plot receptor field. How to model that as a parametric model. So you can, the literature, you can model as a Gaussian, sort of a random field Gaussian model, 2-dimensional Gaussian. or you can model as a zonal key polynomial, which is it's a generalized linear model. This is the basis function, and this is just a regression C as a generalized linear model. So this is to show you an example that's using an orthogonal basis of the Zernike polynomial. You can use in a finite Zernike polynomial to approximate this receptive field. If you use in sufficient number, then probably the approximation will be accurate. So once you construct this encoding, this is part of encoding. You estimate the receptive field, estimate its position, so the state equation position. And the decoding part, basically just sort of doing this point process between the spine train, population spine train, and then come up with the estimated x, which is the position at the end of the red. Okay? Run through this prediction part and the posterior estimated part, is similar to what we showed earlier. And so posterior mode estimate, in this part you're dealing with the Gaussian approximation and come up with the analytical form and the posterior variance. So then, and the result, you can compare the different method, Gaussian, Zernike polynomial, compare the reverse correlation method, and compare different methods have different performance. And you can compare the confidence region and coverage probability, and see this coverage probability. I'll show you a demo.
Excuse me?
Yeah.
How many neurons are considered for decoding?
I think for the hippocampus case, typically the number varies between 30 to, could be high to up 80. But some of the unit could be, had to be primary neuron. In some cases, if it's an interneuron, it doesn't really tell you the information of the space. So you have to really have a very clear receptive field, please receptive field. So a typical recording cover from so this is actually the real data, what we show here. So you can see this Y is it's actually real data, it's the animal position. This yellow part is showing the coverage probability as shown in the slide. And here's, I don't know the resolution is not clear, it's basically up to 37 cells, which is shown here. This is telling the spiking activity here. And this is showing in time how's the performance looks like and tracking the animal position using I think the resolution here is like 2 milliseconds. So every 2 milliseconds update the position. So it's very wide angle resolution. And the result, I mean, it's not, obviously it's not perfect. It's not perfect, but I think in the summary slide you can see the estimate is reasonable compared to the standard method. It's also give you a sort of a good estimate. So the bias could be different, come from different resources. Because of the doing point process filter, we're doing estimation of posteriors in Gaussian approximation. That's one thing. The second is the encoding part has to be accurate. The encoding is doing this position. So the animal is doing this random walk or doing the linear Gaussian, a smooth sort of a Gaussian states model might not be accurate because sometimes animal making a turn, which is like a jump, some sort of discontinuity in which you cannot capture the behavior. So you get the idea, essentially give it the way to do the inference. So I think what it shows here is just a different sort of time to give the mean estimate in terms of the position. And then later on, people are doing, so can we do better? Basically, this extension of using the Gaussian approximation, using some Monte Carlo, so sequential Monte Carlo, to sample from that. So you can use in that posterior as a Gaussian posterior, using as a proposal distribution, and draw a sample from that proposal, and simulate from that, and doing further analysis. And this is a paper basically. They compare using particle filter and simulated and compare the basic sort of white process filter and compare with the combination of the particle filter with the white process filter, a different version of white process filter. This version basically try to avoid the inversion of covariance matrix and rather using a linear way of the try to reduce the complexity. But then you can see different sort of performance comparison. In that specific example, according to the result, that the performance, which is not that, I mean, if you're using a huge number of particles, you can see the performance basically is not much difference. But if you're using a small number of particles, using a good proposal distribution, which is a very, the performance is, the improvement is more significant. The basic is a basic version of white process filter, just using a non-uniformity, sort of a transition plier. It's a very basic version of particle filter.
Okay, now 20 minutes delay, and I'm afraid that people cannot buy lunchbox. Okay, no, but this is the most interesting part, and it's difficult to stop. Let's continue. But fast. A bit fast.
Yeah. So I will be. I have about.
I think it's most interesting.
Right. Because this part has some sort of video stuff like that. So also maybe more intuitive by looking at this data. So that will basically just conclude an example of the hippocampus decoding problem. We can use in this case a basic version of white process filtering to estimate it. Then you can combine white process filter with certain sort of normal cover simulation to estimate sample from that proposal distribution. The proposal distribution could be a Gaussian, which would give you a very efficient way to draw sample, but it probably give you a further improvement about the posterior. So this is another example using an example. This is like primate motor cortex, and estimate is again showing one motor neuron in the different center archive, and then you see different angle, direction, you get different sort of, for one specific neuron was the neural response. Individual row showing one specific trial. Right? So, and for that, we can characterize the tuning curve here as a function of the direction of movement as the firing rate 5 per second, and just the, have a cosine tuning. Then this cosine tuning, you fit the cosine tuning in the parametric form. It could be non-parametric, but you can fit as a parametric curve. And then you write down the state equation. The state equation in this case is the position and velocity. So you can write down that state, augmented state position as a velocity, and write down the state equation. Then the firing property, in their words, actually they're using a spike count. That's the temporal scale they're using, I think it's like 80 milliseconds, 100 milliseconds, something like that. So they count the spike using a Poisson. So basically what they do, the braid is basically you can think of a generalized linear model. So K is a baseline. And D is a unit vector representing the preferred direction. And the V is the velocity. And then you have this part, SI is the, and this I is specific direction, I. And then SI is basically another parameter. Then you deal with the response Y for specific neuron I, then you deal with for specific direction I. Then you have a Poisson, so in a Poisson firing. And then you need to define the lag, and this lag you get during the model selection. You show what's the optimal lag. You need to choose what's the range of the response related to this input kinematic V. So you need to define the lag, what's the informative lag in there, and they do some work to conclude that optimal lag. Basically, unlike the motor cortex, different from sensory cortex, because sensory cortex normally is causal. So essentially, you see the input, then you observe the output. So the output and the input is causal. So basically, you see this input first, then you observe the output. Motor cortex is a little different. Motor cortex it's complex, depends on which area. So people, based on literature, is not necessarily causal. So you can question. So what you see this response, you can relate it to your relate to your sort of like response yt can relate to your velocity t plus certain tau. Tau could be greater than 0, could be smaller than 0. So you need to define the encoding part. You need to define as the range. So it could look like it's non-causal because. So basically, you first have the response trigger. You have the action and trigger the neural response. Basically, what it says. So the tau sometimes you can see the lights could be varying between the negative and positive part. So to define that, typically people define using some sort of information criterion, looking for the optimal time lag to define the encoding analysis. Given the Poisson likelihood, in the world they also impose some smoothness in the velocity, so you can impose some smoothness and you get a second order equation. So basically impose some smoothness. So augment this v and new v, which is the two-dimensional v, vt minus 1. You come up with the augmented state equation. They do some simulation. This is simulation. Assuming the animal running some sort of figure 8 in terms of the trajectory, this is the actual velocity and actual position, and then compare with the standard method population vector, and OLE is the linear regression approach, and compare the particle filtering approach. And you see the performance, obviously. This is, again, so one is the smooth, trajectory is smooth, and second is that it's more accurate compared to the other methods. This is another example. It's also simulation that to compare the circle sort of trajectory and velocity, and the conclusion is similar. Generate the performance more accurate. They also have some real data, but I didn't show here because this is cleaner to show. Eventually, they can compare the overall performance and then summarized by the mean square error. So because we're doing the hippocampus, then sometimes you wonder whether the receptor field itself could be changed according to the experience, right? According to its time variance, non-stationary. So, in a work by Henry Brown in 2001, he characterized the receptor field, hippocampus receptor field as a Gaussian, one-dimensional, two-dimensional Gaussian. So the parameter of theta here, whether the theta can change. If theta change, basically, then you have certain cynetic plasticity. Right? So the question is that, given your spine train, can you actually estimate the theta on time? Sort of like an adaptive filter, run as an adaptive filter. So the idea basically we're using a sort of learning way, just like adaptive filter, LNS filter, using the step side, updated instantaneous log-like loop rather than a log-like loop. Log-like loop will accumulate all observation in time, but because the data are non-stationary, you're showing instead of update the total number of observation, update the instantaneous log-like loop, which is this term. Then you just define the gradient information with respect to the theta, take the gradient of the log-like loop with respect to theta, which give this term, and using the learning way, minimize using the gradient ascent to update the theta. I show you some simulation. So this is the simulation. So you can think the animals here is actually running in the track, linear track, just showing the running back and forth. And here showing the spine train. And then one of the curve, I forgot which one is the real one. I think this one is the real, and the other one following that is the estimate. So estimate the true, it's a simulation, the true, ground true. So you simulate from the ground truth, get a spine train, then you update that based on the spine train, you update the estimate in time. This is the simulation. I'll show you a real data, which is this is change maybe less obvious you don't see the dramatic change as in the simulation. But this is basically is the same thing. You don't have the ground truth now because you don't have the ground truth. You just have the spine train, and then you estimate this whether this receptor field of one specific neuron will change in time. Because this basically animal running back and forth in the linear track, you get more experience when you go on and on, you accumulate experience. And then you see this receptor field depends on the experience or not. And you can define certain sort of the confidence bound and sort of statistical measure for that estimate. Yeah, this is a simulation. Basically, you see a different time point. You can estimate, a different sort of a change at different point. It's clear here. The solution is even poorer. I apologize. So at different point at that specific time, what's the receptive field profile looks like in the simulation? So okay. So another example, you can see that during the single neuron. Tri-variability. So what you observe is a spike raster. Individual tip represents spike. So this in time, this is a trial. So you can see that around trial, the new response increase, right? So when you do a PSDH, you get this. You see the final rate, you characterize average according to tri, you see the final rate basically increase. In the number of spike in the spike trial. So the final rate increase for one neuron. Obviously, it's a non-stationary. You see this, right? So tri-variability, how to calculate this between neuron dynamics. So if you see the PSTH, you average about this all of the tri, you get this profile. Right? So the question is that how to calculate this tri-by-tri change, how to come up with a model. Right? The PSTH doesn't tell you how to even this information, you cannot infer this information. So this graph is not sufficient to tell you what's going on in the data by doing a simple average. So what we do in this Gabrielle in Henry Brown's lab, what she did is basically using a generalized linear model. So model the rate as a certain basis function, as an exponent. Log rate is equal to linear combination of basis function, which is exponential with theta log the other sign. So theta is the parameter associated basis function. The basis function could be an indicator variable. In this case, we cover PSDH. You could use this, a spline function like a cubic spline, which is a third order polynomial. Then you just doing the state equation. Just doing the theta is a random walk. The random walk assumes sort of continuity between the trials, and then allows to be changed. Then you fit, given the state equation and measurement equation, define the spiking property, and using the point process likelihood, define the state equation, measurement equation, you have the likelihood. To the inference, basically try to infer the theta, right? So then, this is showing a summary about how to fit in experimental data, how to fit this trial by time. You can see this is a naive way to estimate the intensity, and this is using the EN, using the step function, EN using the spline function, and compare how to fit. You see, using this tool basically is better than a naive way to estimate intensity. This is a PS2H naive way. So they are not satisfactory according to the KS plot. So what she did is basically not only using Neuronal, using some sort of spike history, incorporate certain sort of previous spike history using certain time window, using up to 9. And then assuming the information, the theta change around tri, and this gamma variable is to tell you the neuron intrinsic property, so it doesn't necessarily assume to be constant. So across trial, this intrinsic property doesn't change, so it's a constant cross-trial. K is the trial index, right? So the performance when you fit that model is still linear, still a generalized linear model. So just unknown variable right now not only involve theta, but also involve gamma. This part is observed, the spike count, the history. So after that, doing this EM type of inference, you get a KS product and see this K fit within the 95% confidence interval. So obviously the performance improved by using another 9 variable in the model. Another example is try to see how to analyze the behavior data. So in this case, the monkey recorded from the monkey hippocampus. So the monkey doing sort of association task. Associators are trained to the car, and there's a 4 target. There are 4 targets in the screen based on the display image. The target and the monkey are trained to base the car in one direction. And then you observe the spiking activity, right? You might observe spiking activity. Also, the error, whether the monkey making the correct or error response based on the saccade, whether it's making the correct decision or right decision. So the goal of that analysis is try to estimate learning curve to characterize performance as a function of the trial in terms of the learning. How does the learning so try by the learning performance probability. Now, what will be the statistical criteria that defines the learning? Right? So you can the first step, you can think of it using a logistic question, and it's a simple way without doing state space model. It's a static model, essentially. You refer to the probability pk is the probability correct response in try k associated with the try number and certain sort of a baseline. And then you fit that. It's a logistic question, so it's very easy to fit. It's a static model. And basically those points, this is the trial, and then beginning is wrong, and then there's a bulldog is correct. But in the beginning, also there's a few trial that's correct. So you want to define what's the curve, right? And then you fit this logistic question that is a monotonic curve, and you have a confidence bound of that based on the maximum likelihood estimate. Then you define, so this is the chance level, right? There are 4 targets, so it's the 0.025 is the chance level. Then you define what's the probability of the correct response. You can define certain statistical criteria and say, after a certain trial, the animal start to learn, and then you define the learning sort of threshold. And then you get assessment, fitting the p-value, and then fit the AIC, and this actually, the basic models actually explain data reasonably well. The question is that, can we do better? So, and Anna Smith basically in the lab, what she did is use the dynamic state space model, extend the basic version of the logistic question. You're assuming that because you're assuming the theta can change, those variables can change in the trial. So in this case, you can fit a different sort of you have a different, so basically it's a trial, sort of classified data complex. And you have this is probability correct. So this, again, is not monotonic anymore. Not monotonic anymore compared to the logic static model. So you have a confidence interval, upper bound, lower bound with that curve. And this is the final rate of the specific cell. Incorrect try, correct try. And you define, based on the confidence interval, you can define the upper bound or lower bound a certain thing about 0.25. When the lower bound is about 0.025, then you define, according to the statistical criteria, is the start of learning. So that's the statistical criteria to define the learning. So the advantage of that, basically, this curve is not necessarily monotonic anymore because it allows to be dynamic change. Another example is how to estimate the.
Okay, very interesting examples, but 40 minutes over.
It's at 12:30, no?
Yes, you should stop at noon. Maybe some misunderstanding.
I thought the time you gave me is at 12:30.
Yeah, you should stop after 12, not 12:30.
Oh, I thought
That's
it's
not 10 minutes, 40 minutes over delay.
Oh, I thought
Because I'm sorry, there's some misunderstanding
Yeah,
of.
So I can just like, because you have a slide, I can just, this is a few more application. I can just jump to the concluding, 5 minutes. I want to, unfortunately, I don't have too many slides I prepared, so I should be as mindful. So I want to give you some sort of take-home message, even I cannot go to one example. So the take-home message is that this state-space analysis gives you a principle framework to analyze this very complex dynamic system. It's very suited to neural data because they have this stochastic and dynamic sort of property of the data. And you want to develop some stochastic model to characterize the observed data, and then also you can come up with a statistical approach to the model assessment. And then all of it, to go to the example, basically I try to give you example using likelihood approach and Bayesian approach to do the inference and for specific problem. And there's some challenging, and there's some active research topic I can give you some pointer. If you want to discuss offline, I'm happy to discuss with you. One is the model selection, and in this talk I won't be able to discuss this non-parametric approach, the Bayesian approach to model selection. And we're talking about some sort of optimization, sort of bound optimization. And those bound is a non-data independent bound. So ideally you want to come up with some data dependent bound for this approximation. And then there are other sort of extensions, sort of like during the practical issue, whether you have the variability in the subject, then you probably want to come up with a random effects model, or during the observation, typically during with the observation might not, you don't have to observe continuously, you observe intermittent observation, and you might just want to consider that extension. And one of the goals, basically, in the inference is trying to exploit the structure of data of the system, whether it's convexity or smoothness or the sparsity, and impose this prior of the knowledge will basically help you to exploit the structure and come up with a better optimization scheme. And eventually, in the end, so basically you want to, for the application, the neural science application, whether it's a very translational application, you really need to depends on narrow your objective, and the analysis sometimes can take different route rather than sort of because you have during the practical issue, your solution could be very different. So, for example, the BMI study, you might come up with some biased by sorting algorithm, or without even relying on spice sorting to come up with the BMI curves, because you're not dealing with the care about the single neuron response. You only care about the population response. So yes, so I probably just stop here.
Thank you very much.
I apologize that I cannot
We will begin 1:40, 10-minute shift. That's okay. 下でお弁当売ってるんですけど、もうないかもしれません。で、我々は彼と中華に行くんですが、全員で行くことはできないので、あとは皆さんで頑張ってください。前の市役所でもご飯が食べられて、そろそろ空いてくる頃です。それから市役所の下のとこに、市役所の中に組み込まれて、コンビニがあるので、そこでもし弁当がもう終わってたら、おにぎりが買えることは買えます。あと裁判所の下にも食堂があるんですけど、ちょっと怖いんで私は行ったことがないです。裁判所の下はあまりないかもしれない。ということなのでよろしくお願いします。はい。